In Chapter 2, we're going to be covering the structure of the atom and the periodic table. We're going to start out by defining elements and atoms. So the definition of an element are, of course, all of the elements that you see on the periodic table. So in this chapter, we'll be starting to familiarize ourselves with the periodic tables, the elements, and the trends. So elements are composed of atoms, and all the atoms have the same atomic number, which is the number of protons of all other atoms of that element. Now I know that is a confusing definition. When we looked at the definition of elements in Chapter 1, we said that it was the smallest unit that could not be broken down any further by chemical means. Okay, so what we're trying to do is build off of that definition now and talk about elements in the form of atoms. So let's move down to the definition of atoms, and we'll get back to what exactly atomic number and protons are to help us understand the definition of elements further. So with atoms, atoms are the smallest particle of an element that retains the properties of that element. So basically, elements are made up of atoms. So let's look more closely at an atom. So what is an atom made up of? Atoms are made up of 3 subatomic particles. Those 3 particles are protons, neutrons, and electrons. For protons, protons are positively charged, +1. Neutrons are neutrally charged, hence the name neutron, so they have a charge of 0. And electrons are going to be the negatively charged particle, having a charge of -1. So let's look a little closer at the structure of an atom. So we know now that it's made up of protons, neutrons, and electrons, but where are those subatomic particles located? So you can see in this representation of an atom, we have electrons being the green dots, orbiting around, following different paths. We have protons and neutrons in the center. So those are the red and blue spheres that you see in the center of that representation. So the protons and neutrons are actually in that center, and that center is called the nucleus. So what the nucleus is it's a small, dense, positively charged region in the center of the atom. It consists of the 2 subatomic particles, protons and neutrons. The electrons are orbiting around that nucleus, around that center, around those protons and neutrons. Electrons have a very low mass, and they're those negatively charged particles, and so they're surrounding that positively charged nucleus. Due to the fact that the nucleus is positively charged because of the protons, and the electrons are negatively charged, they're actually attracted to each other, which helps make the electrons orbit that positively charged nucleus. So looking closer at the nucleus of an atom, so I just said it was positively charged, so let's look at why. Well, first off, the atomic nucleus consists of what we call nucleons. And all nucleons is another word that includes both the protons and neutrons. So protons and neutrons are located in the nucleus. They are also referred to as nucleons. This makes the nucleus a positively charged center. Why? Well, let's look at what it consists of. The nucleus has protons and neutrons in it. Well, protons are positively charged, and neutrons don't have a charge. So overall, that's going to make that center, that nucleus, a positively charged center. So here's just a table summing up some properties that you need to know of the 3 subatomic particles. So the electron, often represented with this E-1. You'll see me write shorthand on the board when I'm doing problems on the board. When I write E-1, I'm talking about electrons. Their charge is -1. The mass is 5.4 times 10 to the -4th. No, you do not have to remember that mass. Okay. You'll notice that the mass is very small. From what we learned with scientific notation, if you have a negative exponent, that means that the number is very small. So we would have to take this decimal and move it 4 times to the left to get it in normal notation. So since the mass of an electron is so small, it's actually negligible. What that means is we count the mass of an electron as being 0. So we don't need to remember this arbitrary number of 5.4 times 10 to the negative 4th because we're just going to say, compared to the other subatomic particles, an electron's mass is 0. So looking at a proton represented by this p to the plus power, it has that plus sign because it has a positive 1 charge. Its mass is 1 AMU for our purposes. The neutron, the other subatomic particle represented in the nucleus, is represented by this n to the 0 power sign because it has no charge, 0 charge, and it also has a mass of 1. So when we're talking about an atom, the mass of an atom is dependent upon neutrons and protons only. Since electrons' mass are so small, we don't count them when calculating the mass of an atom. So next, let's look at atomic symbols and how to represent them. So atomic symbols, like the one shown here, are also referred to as nuclide symbols. So I will call them nuclide symbols quite often during class. So how do you write a nuclide symbol and what is represented in a nuclide symbol? Where you can see by this letter X, that is where the element symbol is going to go. So the element symbols can be found on the periodic table. So depending upon what element you're talking about, that symbol is going to change. Carbon, for instance, has a symbol, is represented by the symbol letter C. So we would put a C where that X is. Next, in a nuclide symbol, we write the mass number where this letter A is, and the atomic number will be where this letter Z is. So what exactly is the atomic number? Well, the atomic number is the number of protons that element has. And the number of protons is going to remain the same for that specific element no matter what. So we can actually get this number, this atomic number, this number of protons from the periodic table. And I'll show you where that's represented in a moment. The letter A, the mass number. So how do we figure out the mass number? Well, this is actually a whole number, and we figure that out or calculate that by adding the number of protons, which we can get from the periodic table, to the number of neutrons. Because remember, mass is dependent just upon protons and neutrons. Electrons are not counted when calculating mass because their mass is so small. Sometimes there will also be a charge on a nuclide symbol. We won't often see that in this course, but it's important to mention. If there is a charge, it's going to show up in this upper right-hand corner that I'm circling here. And then to figure out the charge, you're going to take the protons, which are positively charged, subtracted by the electrons, which are negatively charged. Let's look at an example. So here would be an example of a nuclide symbol. So we can glean quite a lot of information off of this symbol. First off, using the element symbol C, we can figure out what element is being referred to. In this case, carbon. Also, since it gives us Z, the atomic number, we know how many protons carbon has. We could also figure that out by looking at the periodic table and seeing that carbon is the 6th element. Last piece of information given to us, the mass number. So what this tells me is the mass number is 12. Since I know the number of protons, which is 6, I can figure out the number of neutrons. And that's oftentimes what we're going to use these nuclide symbols for, is calculating the number of neutrons. Notice also the absence of a charge in this upper right-hand corner. So if there is no number there, then the charge is 0, meaning that it is a neutral atom. So let's look at some more nuclide symbols and use them to calculate the number of protons, neutrons, and electrons. So given this nuclide symbol, let's figure out how many of each subatomic particle are present in this atom. Well, first off, we know it's a chlorine atom because of the atomic symbol Cl. To figure out the number of protons, we're looking at this number in the bottom left corner of the symbol. So there are 17 protons in chlorine. This number 35, this is the mass number. So we're going to use that number to figure out the number of neutrons. So the nice thing about nuclide symbols is to figure out the number of neutrons, you simply take the mass number and subtract the number of protons. And those are lined up perfectly in a nuclide symbol. So you take the mass number of 35, subtract the number of protons, 17, to figure out the number of neutrons. But we also want to figure out the number of electrons. So to do that, we're going to look to see if there's a charge on this particular nuclide symbol. Notice there isn't one. So if there is no charge and the atom is neutral, that means that the protons and electrons must equal each other. They must be the same. Because protons are positively charged, electrons are negatively charged, so there needs to be the same of both for those charges to cancel and the atom to be neutral. So the answers for that nuclide symbol, the number of protons, electrons, and neutrons, are now appearing to the right. Let's try another one. So this time we have magnesium. So let's start with the number of protons given to us in the bottom left-hand corner. So there are 12 protons. To figure out the number of electrons, so looking at step 2 here, we look to see if the atom is neutral. And it is. So if the atom's neutral, that means the electrons equal the protons. So there will also be 12 electrons. Last step, step 3, to calculate the number of neutrons, we need to take the mass number, which is 26, and subtract the number of protons, which is 12. That will give us 14 neutrons. So why do we need to use nuclide symbols, and what exactly do nuclide symbols represent? Well, they're actually representations of what we call isotopes. What an isotope is are atoms of the same element that are identical in atomic number, but not mass number. So what that means is if I have a carbon atom, all carbon atoms are going to have 6 protons, no matter what. That's the atomic number. That number cannot change. If we change the atomic number, we're changing the identity of the element. However, out of all those carbon atoms with 6 protons, the mass number can change. So we can have carbon atoms with different masses. And this is because the neutrons are changing. So if the neutrons change, the mass number is going to change. Because remember, mass number is neutrons plus protons. Each element on the periodic table has naturally occurring isotopes. So they will have more than one isotope, so different atoms with different mass numbers. So let's look at some ways that isotopes are represented. We've already seen one and actually calculated subatomic particles based off of the nuclide symbol. So remember that isotopes are atoms of the same element with different masses. So looking at the nuclide symbol representation of hydrogen isotopes, you can see that there are 3 different isotopes of hydrogen. Notice that the number of protons in the bottom left-hand corner is the same for each of those hydrogen isotopes because the number of protons cannot change. Otherwise, we would no longer be talking about the element hydrogen. What does change, however, is the mass number represented in the top left corner. So one isotope has a mass of 1, the next a mass of 2, and the last a mass of 3. This is due to the neutrons changing. Another way to represent these three isotopes would be to write out the name of the element itself rather than just the symbol. So we would write out hydrogen and then a dash, and the number that comes after the dash is representing the mass number. So you can see the format: element name, dash, mass number. So once again, all three hydrogen isotopes are represented using that format. Keep in mind, each hydrogen isotope has the same number of protons, but different mass numbers. This is due to the different number of neutrons located in each of those atoms. Here are some practice problems that we're going to do in class. We're going to write the nuclide symbols and calculate the number of protons, neutrons, and electrons. So you can see these are all representations of isotopes, as we saw on the previous slide. Next, we're going to look at Dalton's atomic theory. So Dalton postulated several different things in his atomic theory, some of which are still true and a few that are not, because chemistry is always changing, we're always figuring out new things, and sometimes old theories are disproved. So let's look at these postulates. The first one is that all matter consists of tiny particles called atoms. That is true, and it is still true today. All elements are made up of atoms. The second one, an atom cannot be created, divided, destroyed, or converted into any other type of atom. So this one is actually later proven false, as you'll see by the note down at the bottom. It's not true now because of radioactivity and nuclear chemistry. Postulate 3 says atoms of a particular element have identical properties. Now this is the one I wanted to focus on since we just got done talking about isotopes. This one is also no longer true because now we know about isotopes. So the reason it's not true is because of this word identical. All atoms of the same element are not identical because we just said they can differ in their mass number. They can differ in the number of neutrons they have. The rest of the postulates are still true. Atoms of different elements have different properties. Number 5, atoms of different elements combined in simple whole number ratios to produce compounds. So all this means is later on when we look at chemical formulas, you'll see that when atoms combine, it's always whole numbers. So these subscripts represent the number of atoms that are in that particular compound. And you'll never see half an atom combined with 3/4 of an atom. Looking at number 6, chemical changes involve joining, separating, or rearranging atoms. Also still true. Now let's look at the periodic table. So with the periodic table, we have two scientists who came up with it or helped the process, Dmitri Mendeleev and Lothar Meyer. Now Dmitri Mendeleev gets most credit for it. They were actually both working on it independently at the same time and came up with a similar periodic table, proving the great organization of the periodic table that we still use today. Now the periodic table is listed by increasing atomic mass. So if you're looking at a periodic table, you'll know it goes in order of the number of protons and the order of the atomic mass. It's also arranged so that elements with similar chemical properties are grouped in the same column, and we'll look at that more closely as we go on. The noble gases, for instance, are in the very last column of the periodic table. These noble gases all share the same property of inertness. What this means is they're unreactive. So if you'll look at the periodic table and see that in the last column, helium is the first noble gas in that last column. And that's an element that you might recognize because helium is often used in party balloons. The reason it can be used in party balloons is because it's inert, it's unreactive. If the flame from the candles get near it, it's not going to blow up. Later on, the periodic table arrangement was later justified by the sequential order of the atomic numbers. Remember that atomic numbers is the number of protons present in the atoms of each of those elements. So here's our first picture of the periodic table. I have also posted a periodic table that you could use on the exams if you would like to print that out and have a paper copy to follow as you're working through assignments and exams. So looking at this colorful periodic table, I was just talking about columns. So remember, columns are going to be up and down. We just talked about this last column, the noble gases, that starts with helium here. These columns are referred to as groups or families. The reason they're called groups and families is because they have similar chemical characteristics. When I talk about periods, what I'm talking about are the rows that go from left to right, just like you're reading a book. Notice there are 7 periods in the main part of the periodic table, and that's what we're going to focus on. We're not going to really look at the elements that are down here unless we get into radioactivity in Chapter 9. So here's a picture of the periodic table that I have posted on Blackboard. So what I wanted to point out with this periodic table is you have the periods once again listed 1 through 7 off to the side here. But you also have groups. So what I mean by groups, going down a column. So this first one, these first 2 groups or columns are representative elements. Then we skip over to where boron starts, and these are the other representative elements. So these representative or main group elements we're going to often refer to when we start talking about bonding and valence electrons. So you need to know where the representative or main group elements are located. We'll also talk about the transition elements, which is this group present right here. So here's a list of some special groups present on the periodic table. So in the previous slide, I showed a periodic table and showed where the representative elements were, the main group elements. So among them are the alkali metals in group 1A, so it's going to be that first column present on the periodic table. All of those elements are the alkali metals except for hydrogen. Okay, so hydrogen is not included as an alkali metal. It's actually not a metal at all. It's a nonmetal. Next, in the second group, group 2A, are the alkaline earth metals. Skipping way over to group 7A or 17 are the halogens. So this is the representative elements right next to the noble gases. The last group, which we've already talked about, starting with helium, in group 18 or 8A are the noble gases. So all of these special groups are present in those representative elements. The other special group that we're going to mention is that B section where the transition elements are, and those are actually already labeled on the periodic table in the previous slide. So next what we're going to look at are where the metals, nonmetals, and metalloids are. Keep in mind that metalloids are often referred to as semimetals as well. Those two terms can be used interchangeably. So here's a color-coded periodic table pointing out exactly which elements are metals, metalloids, and nonmetals. So you can see that we have a green zigzag line here. The green elements are the metalloids or the semimetals. On your periodic table, hopefully you have it printed out, you can even draw it here, you'll actually see a bold zigzag line exactly where I'm drawing this red line. So the reason that bold zigzag line is there is because it is trying to separate the metals in blue from the nonmetals in yellow. Notice everything touching that line is a metalloid or a semimetal except for aluminum. Aluminum is the only metal that is touching that line. So knowing where that zigzag line is going to help you figure out where the metals are, all the metals being to the left of the zigzag line, with, of course, the exception of hydrogen. All the nonmetals will be to the right of that zigzag line. And then every element touching the zigzag line is a metalloid. What you will see here are some elements from the periodic table. We are going to label them as a metal, metalloid, or nonmetal, based off of where they are on the periodic table. So if you want to do that, I would go ahead and pause it here, see if you can identify them, because the next slide will give the answers to each of those. So you can see the answers for each of these elements. We have the first list here being the group or family that they are in. So notice germanium, is the only element in this list that does not have a special group. So we simply listed the number or column that it is present in. The other elements present were in a special group, so we labeled those accordingly. The next list shows whether they are metalloids, nonmetals, or metals. Now we're going to look at how an element is represented on the periodic table. So far all we've seen is a nuclide symbol, and the nuclide symbols are not the same representation as we see on the periodic table. So on the periodic table, you'll see we have the element symbol. Oftentimes we have the element name under the element symbol. The atomic number, which is the number of protons, is represented above the element symbol. Whereas in a nuclide symbol, we always had it in the bottom left-hand corner. So now it's flipped and we have it up top. We also have a new piece of information that we haven't seen yet, and this is the average atomic mass. So notice for carbon it's 12.01. It's a decimal point. So far what we've seen is mass number, and those have been whole numbers. So what you see on the periodic table is not the same as the mass number, it's actually an average of all the mass numbers of the atoms in that element. You can see another example below using molybdenum. So here we have the same format with the protons represented on top, the average atomic mass on bottom. The only difference with this representation is the element name is in a different spot. So it really depends what periodic table you're looking at, but the things that do stay consistent are the atomic number, the number of protons, is always a whole number above the element symbol, and the average atomic mass is always a decimal number represented below the atomic symbol. So here we have an early model of atoms. So you'll notice that it's mostly empty space. The nucleus is still present in the center, including the protons and the neutrons, not shown here, and then the electrons were spread around. Bohr later discovered that it was actually a much more complicated structure of an atom than that. So you'll see off to the right, we have another representation of an atom. So we have the nucleus in red, the dense center with the protons and neutrons, and then we have electrons orbiting around the nucleus. So it actually was shown by Bohr that there's more than one level on which electrons are located. So that's the reason that there are 3 circles around this nucleus in this representation. These are the electron energy levels. So how did he know that there were electron energy levels? Well, he actually ran experiments exciting those electrons, and he proved that electrons could actually jump from one level to another. So I'm going to bring you to the top picture, the top diagram here, and this is actually just a cutout of these electron levels. Okay, so this bottom level here would be the energy level closest to the nucleus, and then we would have the next ring up, so on and so forth. So when an electron is excited, it can actually jump to the higher levels. When it does that, how do we know it does that? Because what goes up must come down. So when that electron gets to a higher energy level, it's eventually going to relax back down. When it does, it needs to release the energy that it absorbed, and it does that in the form of light. So we actually see colors emitted when those electrons relax back down. Here is a visible spectrum of some of the experiments that Bohr did to prove that there are several different energy levels to which electrons can jump, because when they do absorb energy and jump to a higher energy level, once they relax back down, we see the colors represented in these emission spectra. You'll notice off to the left-hand side, there are element symbols. So these spectrums are all representations of these different elements. So why is this useful to us? Well, it's useful to us because we need to explain some of the quantum numbers, because quantum numbers are going to help us represent different atoms using electron configuration. And in order to use electron configuration, we need to know about these quantum numbers. So the principal quantum number, represented by the letter N, is actually those energy levels we just saw, those orbits, those rings around the atom in which the electrons are present on. So it is the main energy level of the electron. They're regions where electrons can be found. So the lower that N value, the closer to the nucleus and the lower the energy level. We will see the principal quantum number represented on the periodic table. So looking at the periodic table, remember when we talked about periods and we said there were 7 periods? I have circled here in green. Well, those are your N levels. N equals 1, N equals 2, N equals 3, N equals 4, so on and so forth. This is going to help us identify atoms in the periodic table. So using the principal quantum number on the previous slide, we can figure out which period the element we're trying to describe is in. But we need to narrow it down even further. So in order to do that, what we're going to do is we need another piece of information, and that's going to be the angular momentum quantum number. So the angular momentum quantum number is a sublevel that denotes shape. And this is actually going to narrow down or put the periodic table into further groups. And we're going to designate these groups as S, P, D, and F, represented for the orbitals that they are representing. So S orbital, P orbital, D orbital, so on and so forth. When we're talking about orbitals, the S orbital is going to be the lowest in energy. P will be in this middle. D will be the highest level energy. So where are these orbitals represented on the periodic table? Well, we said the principal quantum number were these numbers off to the side here, 1 through 7. So that will tell us which period we're looking in. Well, the angular momentum quantum number, we're going to look from above. So what that means is we're going to look at the columns. So these first 2 columns here, these 2 groups of representative elements, represent the S orbital. Notice this denotation of N sub S. The P orbitals are going to be the other group of representative elements on the far right of the periodic table. So this will be the P orbitals, designated by this NP. The D orbitals that we talked about, which have the highest energy level, are going to be the transition elements, so this D block right here, represented by this N-1D. The f orbitals are down here in the lanthanides and actinides section. We will not be using those until we get into chapter 9, so we can ignore them for now. So what we have now is we can figure out the row or the period that we need to look in. If we have the n value, it will tell us to look in period 1 through 7. Next, we can further narrow it down by knowing which group to look in. Are we looking in the S block or the P block or the D block, which is going to help us further narrow it down. Let's look a little closer at these atomic orbitals, because remember, the S, P, and D letters that we just looked at represent orbitals. Now, what an orbital is it's a sublevel that contains a maximum of 2 electrons. The s orbital, represented by this green sphere, has just 1 orbital. Since we just said each orbital can hold a max of 2 electrons, that means that the s orbital can only hold 2 electrons. Looking at the p orbital, so it is dumbbell shaped, looks kind of like a peanut, represented by these 3 purple orbitals here. So notice the p section has 3 orbitals. So since each of those 3 orbitals can hold 2 electrons, that means that the p section can hold a max of 6 electrons. Next, let's look at the d orbitals. So in blue here, we have the d orbitals represented. Notice there are 5 of them. So if each of those 5 orbitals can hold 2 electrons each, to figure out the max, we would just take those 5 orbitals times 2 electrons. So the max the d can hold is 10 electrons. Well, let's look at how that's represented on the periodic table. So remember, we said that these first 2 groups of representative elements represented the s orbital section. We just said that the s orbitals can hold a max of 2 electrons. So if we know how many electrons are in the s, that will tell us exactly what element we're talking about. For instance, the alkali metals in group 1a here will have 1 electron. The alkaline earth metals in group 2a will have that second electron that can fit in the s orbital. Let's move over and look at the p orbitals. So in the p orbitals, we said that they could hold 6 electrons. So let's count how many groups there are in the p section. 1, 2, 3, 4, 5, 6. So notice there are 6 groups in the p section, and that's not a coincidence. The p orbitals can hold 6 electrons. So if we know how many electrons are in the p orbital, we know which specific group we need to be looking in. Last but not least, let's look at the d orbital section. So how many groups do you think are in the d orbital section? Remember, we said d orbitals could hold 10 electrons. So you can bet that there's going to be 10 groups or columns in the d section, which indeed there is. Kind of hard to write with this. Sorry for the sloppy writing. All right. So why are we doing all this? Why are we learning all of this? Because we are trying to write or represent atoms using electron configurations. So the quantum numbers we looked at, they're actually used to describe electrons specifically. We know where protons and neutrons are. They're in the nucleus of an atom. But sometimes we want to know or guess or narrow down where the electrons are. So electron configurations are going to provide a shorthand method of giving a description of all the electrons in an atom. And if the atom itself is neutral, it can actually point to the identity of the atom as well. It's important to note that electrons always go to the lowest energy configuration possible. So here's a representation of electron configuration. So the first number represented, in purple here, this number 1, that's representing our principal quantum number. That tells us which period to look in, which row. The letter that comes after the number, in this case S, that tells us which subshell to look in. Are we looking at s orbitals? Are we looking at p orbitals? Are we looking at d orbitals? So that will help us narrow it down to which group we need to look in. Next, we have a subscript after the letter designation. And what that subscript is, it's the number of electrons in that particular subshell. So this is telling us that we need to go to period 1. We need to look in the s block, and we need to go to the second element present in the s block, because that second element present in the s block is going to have 2 electrons. So what this just described is it said, look in period 1, go in the s block, which is this block right here, and it's going to be the second element in. So notice the first element is hydrogen, so we're not talking about hydrogen. Hydrogen would be represented by 1s1, because it's the first element in the first period in the s block. So the element we are talking about is actually helium. So I know helium's over here. The reason it's over here is because it's a noble gas and it has the same properties as other elements present there. But helium, in the case of electron configurations, belongs right here next to hydrogen. So the electron configuration of helium is 1s2 because it's in period 1, it's in the s block, and it is the second element in the s block. So here's a summary of electron configurations. So for electron configurations, if you determine the total number of electrons in an atom, so for neutral atoms, which is what we're going to focus on, remember we said that the protons, the atomic number, is going to be equal to the electrons. So if the atom is neutral, the positives and negatives have to cancel out, positives being the protons, electrons being the neutrons, so they're going to be equal to each other. So if you know the number of protons, you can know the number of electrons. Then you start filling electrons in the 1s orbital first. So the reason we do this is because the 1s orbital is the lowest energy level. Remember, S has a lower energy than P a lower energy level than D. Keep in mind that each orbital can hold a max of 2 electrons, and we looked at that on a previous slide when we said that s orbitals have just 1. Since they have 1 orbital, they can hold a max of 2 electrons. The p sublevel has 3 orbitals, meaning 2 electrons can fit in each of those 3 orbitals for a total of 6 electrons. The d sublevel has 5 orbitals, 2 electrons in each of those 5 gives us a max of 10. All of this is going to help us when we are writing out electron configurations for neutral atoms. So here is an electron configuration representation of the element nitrogen. So you can see by the represented symbol N, we are talking about nitrogen, which is number 7 on the periodic table. So how do we figure out the electron configuration of nitrogen? Well, it's a neutral atom in this case, so the protons are going to equal the electrons. So looking at the protons of nitrogen, the number right above the symbol, we know that it has 7 protons. Since it's neutral, that means it's also going to have 7 electrons. So let's keep that in mind as we go. Whenever we start writing an electron configuration, we always start at the lowest energy level, which is going to be period 1. Once we're in period 1, we write the letter 1, denoting that that's the period we're in, the first main shell. What we hit first is the S block, where hydrogen and helium are, the lowest energy of the orbitals. So we'll write 1s, saying we are in period 1 in the S block. Now we want to go all the way through period 1 because our goal is to try to get to nitrogen. So in order to go all the way through period 1, we need to go to the 1s2. So the reason we wrote 2 here is because that's the maximum amount of electrons that can fit in the S block. So at 1s2, we are now at helium. But we want to keep going because we're trying to get to nitrogen. So next, reading left to right, just like in a book, where we hit next is period 2. So that's why we're writing the number 2, representing that we're in the second main shell. Notice we hit the S block first, where lithium and beryllium are. We want to go all the way through the S block, so we write 2s2, representing beryllium. So we're saying now we're at beryllium, but we want to keep going. So we continue on through period 2, and we hit the P block. We represent that by writing 2p. We're saying we're in the second main shell, in the P block, the P subshell. Now, nitrogen is present in this P subshell. So to represent nitrogen, we just count how many in nitrogen is into that P block. So boron would be 2p1. Carbon would be 2p2. Nitrogen, since it's the third one, is represented by 2p3. So this is the full electron configuration of a neutral nitrogen atom. Notice here is the periodic table with electron configurations put in. So you can see hydrogen is 1s1, helium is 1s2. The one we just talked about was nitrogen. So the last numbers and letters represented in that electron configuration was 2p3. So you can use this to help check your work.